Hi everyone, my name is Hesham Eraqi and it's really my pleasure to be your instructor in this course. Let me start by introducing myself. I have graduated from this department, Cairo University Communication Engineering Department in 2010, and I did my master's there as well. And after graduation, I have been working in teaching at AUC, the American University in Cairo. And nowadays, I am an adjunct faculty in the Computer Science and Engineering department. Since graduation also, I have been working in automotive industry. It has been more than 8+ years now. I am a senior expert of artificial intelligence at Valeo. And let me tell you more about Valeo. Valeo is an automotive supplier. And as an automotive supplier, we supply car makers like Mercedes, like BMW, Hyundai, with technology products. When you buy a Mercedes car, most probably the air condition control system is not done by or manufactured by Mercedes. Mercedes most probably has bought this from an automotive supplier like Valeo. And this is why, by the way, automotive suppliers, the name of the companies might be not very popular to normal people from outside engineering in general, because the customer for automotive suppliers is car makers. So automotive suppliers will not for sure do a commercial for you in TV. You are not the customer, but everyone know Mercedes, everyone know BMW, because they are car makers, and we are the customer of these car makers. So at the end of the day, Valeo is a factory, and I can see this factory having 3 pillars. The first one is mechanical work, to do haptic motors, to do potentiometers, to do LEDs, to do maybe plastic covers, mechanical work. The second thing is hardware. The third thing is software, and Valeo Egypt is only working on the software part. It is the biggest R&D site for Valeo worldwide. In this site, it is the only site for Valeo that combines all Valeo product lines in the same site or the same building. So you will see people who are developing wipers, car wipers components at the same building, with people who are working on exterior lighting, interior driver monitoring, or people who are working on active safety features, autonomous driving, all in the same site. Valeo Egypt at the moment is having more than 2,000 engineers. And to give you some idea about how important Valeo is, the most company that was filing patents for the last year and the year before it and the year before it, for these 3 consecutive years in France, the top French patent filer is Valeo. And here I'm not speaking about automotive industry or maybe software industry or anything. I'm speaking in general. So this can give you some idea about how big Valeo is. And the good news is that, speaking about the fact that this course is a machine learning course, the good news is that Valeo Egypt is now opening 2 new sites, and there are lots of opportunities for data science and machine learning engineering you can find at the website valeo.com. You can choose careers. It will ask you which region. You choose Egypt, and you will find all the available jobs are there for you. Yeah, so all of my filed patents journal conference papers, book chapters I wrote are in the area of machine learning and autonomous driving. I think we can start, and I would like to thank you so much for your engagement during our previous online session, and I wish this video recording helps you understanding the concept. Today we will talk about unsupervised machine learning. So during the last lectures, we covered the supervised learning algorithms like SVM, things like this. And for this, you need your data to be annotated. And we know that annotation is the most costly stage or step in the process of machine learning development. So if you want to save this cost, you can use unsupervised learning. So let me share screen with you. I will be sharing my entire screen. And this is our presentation. So it's about machine learning clustering. We will talk about an introduction. We will continue the classification of the machine learning algorithms and the supervised, the unsupervised algorithms. We will talk about the clustering algorithms that we are going to discuss. We have distance-based clustering algorithms. We have dynasty-based clustering algorithms. We have hierarchical clustering, and we have soft clustering. And after we finish discussing about these clustering algorithms, we will discuss the clustering validation, or how can you measure if a clustering result is good or bad. So let's continue regarding the introduction. We have the supervised learning. We have unsupervised learning. We are going to cover it today. And it is, in my opinion, it is more near to the way we as human learn, because at the end of the day, if you have a child and you leave it in a room alone without any supervisor who gives him a label to the objects, he will be able to learn at the end of the day, and he will be able to do a representation for the environment, the objects he have in the environment, and he will be able to use some objects in the environment and interact with them. He will be able to know by himself alone the differences between the different objects and how can he put them in useful ways. But if at some moment that child is exposed to the outer world, the knowledge or the representation he have might not be very useful, because he is missing what we name as the fine-tuning. He needs someone to tell him that thing that you used to stay is named chair. That thing or that class you used to put your things on is named a table. So someone should give him the names of the objects that he already learned to do representation for. Again, it is subjective opinion. You might agree or disagree with it. And I think we discussed this later, and some of you was disagreeing with it. Again, it is subjective matter. So supervised learning is already covered, and we will cover it in coming lectures, inshallah, when we talk about deep learning and neural networks. But today we are going to discuss unsupervised learning, and I think at the beginning also of the coming lecture. The third type from this classification point of view of machine learning algorithms is the reinforcement learning machine learning algorithms. And because you will not hear about reinforcement learning again, and we didn't hear it about it before, so I wanted to zoom on reinforcement learning algorithms in this lecture, so you have an idea about how it works, how it is different from supervised and unsupervised learning. In supervised and unsupervised learning, we have data, and this data can be labeled in case of supervised or unlabeled in case of unsupervised machine learning. But in reinforcement learning, there is no explicit data that you have in hand. You have an interactive environment, and the data is generated by having your agent experiencing this interactive environment. Usually, you need to learn a policy that map from the current state of your agent or robot and the action that he might take. And if this policy is good, the agent will learn to take good actions given any state he might face. So initially, the robot starts from a random state. For example, one of the most famous algorithms for reinforcement learning is the Q-learning. So in Q-learning, the policy is represented in a table that maps states, all the possible states, with all the possible actions. It is named the Q table. The higher the Q value you have, this indicates that this action is preferable because this is the policy represented in the table. Initially, the table starts from having a uniform distribution of numbers. So you have the same value everywhere in the table. And you update your table using a very simple equation that you see. You can see here. Let me choose the laser pointer. Yeah, this is the equation. So initially, the robot starts from a random location in the map or in the environment, in the interactive environment, and he starts from knowing nothing about it. He starts from having a random policy, and according to this random policy, he will choose an action to take. So if it is random, he will, given if the robot starts from state 5 at time t, he will check which action at this stage, at this row of the table, having the maximum Q value. So if the policy is random at this moment, you have the same values for all the row. So he can pick any action AT at time t to take. So assuming he was in state t at time t, he take action AT at this time. So he go to state ST plus 1. And in state ST plus 1, he has many actions, possible actions to take. Okay, so at this moment t, the new, we will update the table using the equation. So the new Q value in this cell of the table is equal to the old value multiplied by a fraction plus some learning rate multiplied by the reward. Let's ignore this discount factor part for now. So the new value is the old value of the table, part of it. So if the learning rate is 10%, 0.1, so the new value will be 90% the old value plus 10% multiplied by the reward. So if the action AT was good, the interactive environment will give you a positive reward, which means that Q new will be higher than Q old. But if the reward value is negative, this means that the new Q value will be lower than the old value. So if the learning rate is 0, your policy will never change. The new value will be the same as the old value. If it is very small, you will find that the policy is slightly changing through learning iterations, so we are not learning in a good base. If it is very high, you will find that you start from a policy, and this policy is drastically changed based on a single observation, which means that you completely change the policy by single observation. So usually you will end up on having not a very good policy. So you start from a bad policy and you end up having not good policy because you should have chosen a moderate learning rate, because the good policy is in between these two policies. And this is why you need to pick up not very small, not very big learning rate value. Okay, So what is the discount factor? What is this term? So if the discount factor is equal to 0, the equation is as we have stated. If it is more than 0, you find that you are not only adding the reward, but the reward plus some factor multiplied by the future of what you are doing, the future of your action. So your action will lead you to state st plus 1, and in state st plus 1 you have several actions to take. Let's be optimistic and take the maximum or q value corresponding to the best possible action in state st plus 1. Okay, so you take this maximum, you multiply it by the discount factor, you add it to the reward, and this is your learned value or combined reward that is future looking. So if the discount factor is 0, the robot or the agent will be short-sighted. It will take actions that maximize his current reward. But it might be that if he take a different action, that different action will lead to a state st plus 1 where you have better possibilities to take. Okay, better actions to take that will maximize the q value. And take care, by adding this discount factor term here, you are making that equation recursive. So st plus 1, q st plus 1, and a is function of q st plus 2, and a is q s2 q st plus 2 is function of qst plus 3, and so on. So the higher the learning, the discount factor value you put, the more the robot will be strategic or long-term sighted. Okay, so this is the Q learning. Recently, by DeepMind, they invented an algorithm which is called DQN, or Deep Q Learning Network. They are representing the policy that maps states to actions in terms of a neural network or a deep neural network, and it's very handy neural network that is very, very successful. Okay. So another example for deep reinforcement learning is what's called the evolutionary neural network, ENN. So in evolutionary neural network, we'll talk about neural networks later on, but you can think of this is a neural network. You can think of it as a black box that has numbers inside it. These numbers are the weights, and you have an input and you have an output. And this black box takes the input, multiply it by multiply it by the weights, or do some mathematical operations that the weights are involved in. And after this, it gives you the output. Okay, so if the neural network is random, this means that the weights are random. Okay, and if you start to learn something useful, this will be represented on the weights. So in ENN, you start from a random solution. You have a random selection for the weights, and you test it on the problem in hand. Because it's random, it is not a good policy. So if this is a car that is receiving data coming from a laser scanner sensor, it will eventually hit the wall very soon. It is a bad solution to the problem. But let's record how bad it is. Let's record the fitness, the time maybe the vehicle has taken until it collided with the wall, and record the fitness of this solution or this chromosome, that bad solution. So you have a chromosome, the first chromosome, you test it, you record the fitness of it. Let's create another chromosome, which is random as well, and deploy it and record the fitness of it. And do the same using a third random chromosome, and so on. Assume that we have a population size of 100. So we have 100 random chromosomes. We tried them all, we evaluated them all, and we know the fitness of each one of them. Okay, they are bad, all of them is bad, but they are relatively better than each other. So let's do a selection. Let's select, for example, the top 20% performing chromosomes and then neglect the others. And we want to create a smarter generation out of these top 20%. So let's do two operations. Let's do crossover and mutation. Crossover means that you will create new child chromosomes coming from two randomly selected pair of parents from the selected 20% top chromosomes. So each child might have his half of his weights or half of his weights value or numbers from one parent and the other half from the second parent. You have different strategies for crossover. This is might be one naive option of them. And in order to create or do some innovation in the childs and add new properties for their behavior, let's do a mutation. So you can sample, you can select randomly some locations in the chromosome and you put some random values to them. And after the crossover and the mutation, you end up having a new generation of population that if you try the chromosomes in this new generation one by one, you will find that they are performing better on the average than the old generation because they are actually generated from the top of the previous generation. So the good people or the good chromosomes are sustaining and the bad chromosomes are being eliminated. So you expect that the second generation will be performing better than the first generation. So this will be noticed when you calculate the fitness of each chromosome. And after this, you repeat the process. You do selection again, crossover, mutation. You evaluate the new generation, selection, crossover, mutation, until you find that the performance is saturating to a good KPI that indicates that your problem is solved. Okay. So we here use genetic algorithms actually to train neural networks. Unlike if you are going to train neural network in a supervised way, you will train it using the backpropagation learning algorithm, but here we train it using genetic algorithm. We are trying to solve here an optimization problem. Very simply, you have numbers, you have set of weights, and you are searching for the good or the optimal values for these weights that achieve some criteria. So this is an optimization problem, and we solve it using genetic algorithms. And it is known that genetic algorithms solve almost all the optimization problems using moderate performance. But for problem X, you might have an optimization algorithm Y that solve it very efficiently, but it doesn't solve the other problems as efficiently as that. For another optimization problem, you will find another optimization algorithm that can solve it very efficiently, but it doesn't perform as this on the other problems. And the good thing about genetic algorithm is that it can almost solve all the existing optimization problems, but don't expect that it will solve them very efficiently. One example that I did in one of my papers where we used genetic algorithms to learn navigation. So in this very simple environment, the vehicle is receiving as input the input coming from this very simple laser scanner. So this laser scanner is hitting the environment, and when it hits the environment, the vehicle simply is transmitting a laser scanner. The laser scanner is hitting the wall, and it comes back to the vehicle. And because we know when exactly did we transmit and when exactly did we receive the echo, we know the speed of light, so we know there is an obstacle at distance x, and we send multiple beams in different directions, so we end up having like around 20 numbers indicating the distance between the sensor and the green dots you see in this graph. So these 20 numbers are the input to the neural network. They are around 20, I'm not sure about the number. This is the input to the neural network. And what is the output of the neural network? Simply, it is the steering wheel angle. Okay? And what is the objective from this reinforcement learning process is to learn navigation, to navigate without colliding with the road or the wall boundaries. Okay? So generation 0 was very bad. This is the best chromosome in generation number 1. So as you see, it is driving. After 2 generations, a vehicle was driving, but it hit the wall very early. This is the best chromosome in generation number 2. It's trying to learn from the mistakes done by the previous the mistakes that let the previous generation achieve lower fitness value, because lower fitness value will be eliminated during the selection. This is why genetic algorithm is very similar to the biological or the natural selection in nature. So after some time, in generation 8, you can see a vehicle that is able to traverse the whole simulation environment infinitely without colliding with any rules. In that paper also, we tested the collision avoidance. So initially, if you learn the task of collision avoidance, you initially see the vehicles are colliding with each others. After some time, you will find that they are learning how to drive without having any problem. I think I have a problem with the video here. I might send it back to you. Yeah, this is the video. Let's see it. So after learning, they learned to circulate around each vehicle, learned to circulate around itself, because if the fitness is to survive, so I can circulate around myself. This is why I programmatically detected this and penalized this with hand-coded 0 fitness. And after this, they learned to live together without doing any collisions. And by the way, this is one major drawback about reinforcement learning, is that it's very hard to formulate a fitness function that achieves the goals that you have in mind. I think I have some video that I might share with you. I will send it to you after the lecture, but it is indicating or highlighting that concept. It is from a gaming car, a racing game, and the objective is that the vehicle finishes first in the race. And what happens is that the vehicle started to learn to take turbos and to do some drifts, because that is maximizing the score. And when you were formulating the fitness function, some things like this might not be very clear from the beginning. Facts like that turbo is maximizing the score, and from the beginning you might have thought that the score is all about your finishing position. Another drawback about reinforcement learning is that we use interactive environment for training. Usually we do this because we learn safety critical applications, as we are going to see in the coming slide, and we don't want to collect data with bad examples in safety critical applications. If you want to learn lane keeping assist active safety feature, for example, you don't want to collect data where the vehicle is doing bad maneuvers, where it is going outside the road boundary. So using the same algorithm I described, we extended the paper through additional experiment. We wanted to learn lane keeping assist on more realistic simulators. This is car maker simulator, And I actually conducted this research in Stuttgart in Germany, because the license was very expensive and it is not node locked, and I didn't have access to it in Cairo. So the input now is the detected lanes from the camera, and the output is a steering wheel angle. Car maker is very accurate model, provide very accurate model, and as you can see, our vehicle learned to do lane keeping assist, which is an active safety feature that automotive suppliers are selling. So I wanted to zoom on reinforcement learning, because this is the only time in the semester that you will hear about it. And now let's go back to clustering or unsupervised learning. For supervised learning, you need data, and there is a service online called Amazon Mechanical Turk, where you can use to put your data for annotation by the crowd. You will crowdsource the annotation costly or labeling the process. And you can also, if you if you know someone who is searching for work, you can refer him to Amazon Mechanical Turk, where he can use it to annotate data. You will open it very simply. You create an account. You find a button called hits at the top of the website, and you will find all the available jobs. A job for for example, draw a rectangle on the house door. So you have images and you need to draw a rectangle on the house door, and it tells you that for this task, for each image, you get 1 or 2 cents. So you know beforehand how much are you going to earn. And sometimes the hits or the jobs do some test to guarantee that you are capable of you are doing it. You can do it efficiently, I mean. Sometimes they put hidden tests to guarantee the quality of your work, because they don't want to re-annotate the data you annotated to know whether your annotation is good or not, and pay double the cost. And they want to blindly judge your annotation quality. So there are some metrics that might be used in this regard, like how much on the average do you take to annotate a single data sample compared to our expectations, or the expectations of the one who is offering the task for you. If you are doing object detection, how many points do you use to annotate an object in an image as a polygon? Things like this are handy to do blind quality assessment for annotation. Okay, so in clustering, in unsupervised learning, you don't have any data, and clustering is one of the most famous techniques of unsupervised learning algorithms. And you can use it to do analysis of your data, to understand your features or to understand your data. And it tries to split your data into homogeneous groups. And the different algorithms have different definition for the word homogeneous. They are seeing it from different criterion. And the applications for clustering is endless. You can do this. You can do market segmentation based on some data you have for customers, previous purchasing history. You can do market segmentation. You can tell when a customer can do his next purchase. You can do image segmentation. You can subgroup each pixels into a cluster or a class. You can do document clustering if you have lots of documents and you want to cluster them into historical documents, scientific papers, and or books, and so on. The amount of applications is endless. I know some of you are working at Vodafone for more than 9 years now. So I have been teaching a course about machine learning at there, and at the end of the the course there is a capstone project, and many of the projects conducted in this course tackled use cases at Vodafone telecommunication use cases just using clustering. I remember one capstone project was doing the ADSL customer satisfaction. He was estimating that using some features that are there, like the waiting time calls, the line type, whether it is fiber optics or copper, and so on. That was one project. Another project I remember was doing he was clustering the powertrain stations, the BTSs, according to the expected downtime window. So based on the equipment type, some power readings, he can expect that this BTS will fail after 1 day, that other BTS will fail after 1 month. This is the second class or cluster, and so on. And I think, if I remember well, 2 or 3 more projects were using clustering in their capstone project. So the applications are endless. And today we will talk about the first type of clustering, which is dynasty-based clustering. And a famous example it is distance-based clustering. A famous example for distance-based clustering is the k-means clustering algorithm. And it is an iterative algorithm, and it works like this. Initially, you have a data. Please note that color here is indicating the class. So initially, the data is not labeled. You don't have any class for your data. And k-means starting by asking you to provide a variable k, which is the number of clusters that you expect are there in your data. So in this example, let's assume that we provided the k equal 2. So initially, he will pick up 2 random points in space, in the 2D space, because the data here is 2D. Each point is represented by 2 numbers. So he will pick up 2 centroids in this 2D space randomly. It might be smarter to pick up or to do initialization more smartly. We will discuss this later on, but the naive approach is to do it just randomly. So we select 2 clusters because k is equal to 2. This is the first cluster. This is the second cluster. If you see my laser pointer, this is the first one. This is the second one. And after this, it do what we name as the expectation step. So according to this assumption, what do we expect regarding the classification of each point? So each point is checked if it is more near to the first centroid or the second centroid, and according to this, it is classified to the class that makes it near to its centroid. So all of these points are more near to that centroid, so they are classified as red class. All of the other points are more near to that blue centroid, so they are classified as the blue class. Okay, so now we have a red class and the blue class. This is a centroid now of the red class. Can we get a better centroid than this centroid? Can we maximize our expectation that we just did? Yes, because if this centroid moves to the middle of these red points, it would be more representative to the red points cluster. So the second step is to do maximization. So we will calculate the mean of the red points, and this will actually be our updated new centroid of that class, and the mean of the second class, the mean point, and this will be the new centroid of that cluster or that class. And because we changed our clusters centroids hypothesis, we should do the estimation again. So according to these new points, we should redo our points assignation to the different classes. So after this, you will find that our clustering decision has changed. And after this, you do the maximization step. You update the centroids. You will find that they are updated, but slightly updated compared to what happened in the previous iteration. After this, you do again the expectation step. You assign the points again according to the updated centroids. And after this, you do the maximization step. You calculate the new centroids. You will notice that eventually this process will converge, and there is a mathematical proof actually that we are going to cover later that will guarantee the convergence. But it is not guaranteed that this algorithm will converge. If you run it multiple times on the same data, it is not guaranteed to converge to the same configuration or the same solution. And I think you already guessed why is it the case, because you start using random initialization already. So based on your random start, you end up having a solution that might be different if your random start has changed. But it is guaranteed that you will converge in finite time, as we are going to see. So k-means algorithm is an iterative algorithm. It is an example for an expectation maximization or EM machine learning algorithm. And we have lots of other machine learning algorithms that are EM, like the k-means algorithm. Okay. So during the you have two steps, the expectation and maximization, and during the E step you hard assign each data point to a particular cluster, and during the M step you use the Euclidean distance to optimize your model or to update the centroids. Okay. And this is why, by the way, k-means is assuming spherical clusters. Spherical if we are speaking about 3D data, circular if we are speaking about 2D data, 3D data, it will assume spherical, and hypersphere or something like this if we are speaking about multidimensional or higher dimensional data that we cannot visualize. Okay. So if I ask you, how many clusters do you see in this image? Okay. So 6 of you is saying that it is 6 clusters. 1 of you is saying that it is 5 clusters. And let's look to the same data from a different perspective. You will find that from a different perspective, you will change your answer. It is very hard to tell from the start how many clusters are expected to be in your data, and it's very hard to choose the k value before you start. This is why when we discuss later the DB-scan algorithm or the dynasty-based clustering algorithms, you don't define k. The algorithm figures the number of clusters by its own. But if you want to use k-means, you are forced to define k. Are there any guidelines that can help us choosing k? Yes, there are some guidelines. One known guideline is the elbow method. So you start to try. You start by running the k-mean with k equal 1. Afterwards, you try k equal 2. Afterwards, k equal 3, and so on. And at each time, you calculate what's called the total within sum of square. What does this mean? It means that in each cluster, you have a centroid, and you calculate for each point in the cluster the square distance between the point and the cluster centroid. And you add all of this squared, and after this, you will add it for all the different clusters. So it is guaranteed that if you increase the value of k, you will find that the total within sum of squares will be lower. It's guaranteed. But how much do we gain? How much do we find this value decreasing when you increase k? So when you start to increase k from 1 to 2, you notice that you have huge improvement or gain or decrease in the total within sum of squares, because this is indicating that the clusters are more compact. And from 2 to 3, you notice if you still have big gain, it's not as big as the gain before, but at least the gain is considerable. If you draw it in a graph like this, you will find that the slope is almost vertical, still more vertical than being horizontal. And you keep do this until you draw this this graph here, and you will find that this graph is looking like an elbow, like this, an almost horizontal line and an almost vertical line. And you are interested in this joint point between these two lines. And this point in this example is at k equal 4. And this is the optimal point for you can choose as k, because after this you start to get unnoticeable improvement in terms of clustering compactness. This is a nice method that can be used to guide you choosing a good value for k. There are different KPIs. Instead of using the total within sum of squares, there are different KPIs to use to indicate whether the clustering is good or not that you can use. But we will cover this later on when we talk about validation clustering at the end of the coming lecture, inshallah. So two examples of the metrics that you can use is the silhouette coefficient consistency metric. Another metric is the intra-cluster variance. Okay, but again, we will discuss this later on, inshallah. One major drawback about k-means is feature scaling. So what you see now is the same data, but the x-axis feature is at the graph to the left is drawn using seconds unit, because this is time feature, and the graph to the right is using the unit as minutes. And if you run k-means to the graph to the left, you will find that this is the result. So k-means thinks that your two classes, because you predefined k equal to in this example, so it assumes that your two classes are vertically separated. But if you just modify the unit, the scaling of one of the features, you will find that also, please note that the vertical feature scaling is also changed here, not only the horizontal, sorry. So you will find that by changing the unit or the scaling of your features, you end up having completely different clustering. And this does not make sense, because each point should be assigned to a class or a cluster, not based on the units. It should be based on the value that the feature have, not the unit of it. Okay, so this is one problem that you will face if you use k-means. So to overcome this problem, you need to do some sort of normalization or feature scaling. And you can do standard scaling, or you can make it more simple using min-max scaling. So in standard scaling, you assume your data is coming from a uniform distribution, which is a valid assumption in many or the majority of the data we have in life. And before giving your data numbers to the k-means algorithm to cluster, let's do normalization first. So your data points are x, and you will not give your algorithm x, but you will do some normalization, and you will provide to your algorithm the z values. So for each feature, you can calculate what is the mean of this feature. So if you have a feature, for example, for person height, and you have 3 persons, one person is 160 centimeters, another one 170, another person is 190. You can calculate the mean of these 3 samples, and you can calculate the standard deviation of these 3 samples according to this formula and the mean that you have just calculated. And after this, you can standardize the feature or normalize the feature. So the person whose height is 170 centimeters, you will not provide the 170 to the k-means algorithm. But before this, you will subtract the mean value you just calculated and divide it by the sigma value, which is the standard deviation that you have just calculated. And you get z, for example, equal 0.5. So you will give your algorithm as a data point as 0.5 for this feature, and you should do the normalization on all the features you have in your data. And afterwards, if you calculate the mean of the z values of your data, not x, the mean value of, speaking about maybe one feature, the mean value of the x points of that feature is mu. We already calculated. But if you calculate the mean of the z values, you will find that it is 0. And if you calculate the standard deviation of the z values, you will find that it is 1. And it is expected. This is what we wanted from the start. This is why we did the normalization. We subtracted the mean and divided by the standard deviation to force the mean to be equal to 0 and to force the standard deviation to be equal to 1. And can we verify this using very simple Python code? Yes, we can verify this. And at the same time, we will know how to use this standard scalar in Python. So in scikit-learn, you have processing sub-package, and from this you can import standard scalar module, and from NumPy we import NumPy as NP because we need it to create data, and we define using NumPy an array. This is how our array looks like. So it is composed of 4 elements, and each element is composed of two features. Okay, so we have 4 samples, and each sample is 2D. The data is 2D. So we instantiate a scalar from a standard scalar, and we fit transform that scalar on our data, and we get our scaled data. If you print the scaled data, you will find that the data is now transformed, the values are changed, and if you calculate the mean of the scale data, you will find that over the first feature, it is equal to 0, minus 1 plus 1, minus 1 plus 1. And over the second feature also, it is equal to 0. And if you calculate the standard deviation, you will find that it is 1 over the first feature, and it is 1 over the second feature, while the original data was not like this. The mean in the original data was equal to 1 on both the features, and the standard deviation was not equal to 1. Okay, so this is how you can do standard. You can use standard scalar from scikit-learn library in order to avoid the problem with scaling of using k-means. You can also use the min-max scalar instead of standard scalar, and this is simply trying to make your values from 0 to 1. And anything, so the lowest possible value of the feature will be assigned to 0, the maximum value will be assigned to 1, and any value in between will be based on linear interpolation from 0 to 1, and from the minimum value and the maximum value on the y-axis of the vertical, the linear transformation. Okay, so this is the solution for the problem of feature scaling in k-means. So this is a nice website that shows you the k-means process in action. So let's very quickly check it. So in this website, you generate data randomly or whatever. Let's generate it using maybe smiley face. So smiley face is a very challenging problem that cannot be solved using k-means clustering. So let's see how k-means clustering will work. We need to set the value of k. So let's choose k equal 4, which is a good choice for this data. And let's put it as 4. So this is the first centroid. Randomly it was put here. This is the second centroid. This is our third one, and this is our last fourth one. Okay. It's not completely random, by the way, in this initialization strategy, because you notice that they are equally separate from each other. We will come back to this initialization centroid strategy later on. So let's start the first iteration of our k-mean algorithm. So this is the expectation step. So after this, we will run the maximization step. So we expect that our centroids will be changed. So yes, they are changed. And let's run the expectation step. So we will expect that you will have different clustering configuration or clustering output. So let's run the expectation step. Let's reassign the points. This is what this step is actually doing. So some points are reassigned. Let's update centroids. Reassign, update, reassign, update, reassign, update, reassign. We are converging now. Is the problem solved? We converge it, but the problem is solving because it's very challenging for k-means to solve such pattern. Let's select another pattern that might be easier to k-means. For example, what is example A? Yeah, this might be simple. Let's pick up 2 centroids. So this is the first one, this is the second one. Let's go. So, okay, second step. So it converged in 2 steps and the result is very good. Can we add third centroid? Yes, let's. Okay, it converged also very quickly and the result is very good with data like this. Let's take a last example where we have more points, because this example has very small point. Maybe back the circles. It's not that easy also for k-means. Pimbit smiley. I will choose Maximization. Yeah, this is a typical. Sorry. Yeah. This is the typical problem that can be solved easily using k-means. But I won't start. Where is start? Yeah, these are the centroids. Let's go. Update centroids. The problem is solved. Let's restart. We can, by the way, let's select our initial centroids badly. So let's put one here, another one here, and maybe that one here. Will the k-means algorithm be able to recover from this bad setup? Let's see. First iteration. So it was able to recover from it very quickly. And this is an easy problem setup to solve using the k-means. Okay, so it will converge at a finite time, because let's ask ourselves, is it guaranteed to converge? We are trying to answer this question. We want to discuss the convergence proof. If you have endpoints and you want to cluster them into k clusters, how many number of possible clustering configurations that you might have? The total number of possible clustering configurations that you might have, the total number. You will find that that is equal to k to the power n. A very simple example for this is that imagine if you have 2 points and you want to cluster them into 3 clusters. So each point can be cluster 1, 2, 3, and you have 2 points. So the first option of clustering is to have the 2 points for cluster 1. So cluster 1 for 2 points. Or the second point may be cluster 2. So the first one is cluster 1, the second point is cluster 2. The third option is cluster 1 and cluster 3, and so on. So you will find that you are multiplying 3 options by three options. So you multiply 3 by 3, so 3 to the power 2. And if you have 3 points, you will find that you multiply 3 by 3 by 3, which is 3 to the power 3. So it is k to the power n. So we have finite number of possible configurations. And what k-mean is doing is that it is at each iteration, it is definitely at one configuration out of these k to the power n configurations. And it is going from one configuration to the other one. It's going from one configuration to the other one in a systematic way that we have just described. With systematic way here, I mean the way that k-mean is working, the algorithm itself. It is a systematic algorithm. And it is going from one configuration out of one configuration into another configuration out of finite amount of configurations that are possible. And for sure, if you are having a setup like this, while having finite set of configurations, you will find that you will be alternating between the configurations in a repeating pattern, because you have finite set of configurations and you move from one to the other one in a systematic way. So for sure you need to have a pattern that is repeating, because if you start from configuration number 9, this leads to configuration number 6, and you go through several configurations until you go for configuration number 9 again. So because you have a systematic algorithm, when you was in configuration number 9, after this comes configuration number 6. So if you meet configuration number 9 again, definitely you have configuration number 6 afterwards, right? So you should have a pattern that is repeating forever. And the question here is that what is the length of this pattern? So please note that in k-means, each configuration, each clustering configuration has a cost. This cost can be the sum of squared distances that we were measuring, and each configuration has a cost. And definitely you are going, if you use k-means, you are going from a configuration to another one with smaller or equal cost. Okay, so you are improving the clustering while you are going. So you are going from a configuration with a bad or large cost to a configuration with a lower cost. If we add this fact to the fact that we should have a pattern that is repeating, you will find that this pattern size should be equal to 1. Because if this pattern size is more than 1, if it is true, if it is 2, for example, this cannot be possible. Because if it is 2 and you start from, let's give an example. If the pattern size is 2 and you go from configuration 9, and the pattern is like this: 9, 6, configuration 9, configuration 6, configuration 9, configuration 6. Is this possible? We say that each configuration has a cost, and k-means is going from a configuration having bigger cost to a configuration having lower cost. So if it is going from configuration 9 to configuration 6, this means that configuration 6 has lower cost, so it is impossible to go again for configuration 9. So the only solution to this is to have our repeating pattern having its size equal to 1 configuration only that will be repeating. So you will find that iteration by iteration, the algorithm is only repeating the best configuration for clustering that it can achieve. This is some text that describe the convergence proof to read and revisit. So please note, if you are implementing the k-means algorithm, if you're writing a code that implements the k-means algorithm instead of relying on scikit-learn library, you need to take care of two major things. The first thing is that at sometimes you have a centroid, and this centroid does not have any points assigned to it. So it's like an empty cluster, and usually when you implement something like this, your code might involve some runtime errors coming from dividing 0 over 0. So take care of this if you are implementing k-means. Something else you should note is that you shouldn't run k-means one time. You should run it several times, because we know that each time it will converge to an answer, but definitely. But if you start from, for example, these starting centroids, you will end up having this convergence configuration for clustering. If you start from a different centroid, like in this case, you might end up having completely different results for clustering, or you might end up having the same result. So we don't guarantee if we run starting from a different starting point, you should reach different results. In general, it might be the same, because two different random initializations might lead to the same result or not. We don't know. So it is healthy to run your k-means algorithm several times. Scikit-learn, for example, run it 10 times, and amongst these 10 times, he checks the results. He do some very quick validation to check which clustering result is best, and he gives you that best result. So you can rely on the average distance metric. You can calculate the average over all the clusters of the squared sum distances. And in these two results, it is the same. It is 0.3. But in this result, it is 0.6. So the first two results are much better. You should give one of them instead of the first one. Okay. So we have very quickly a workshop about how can you use scikit-learn to do clustering. Let's see. So I will be sharing this code with you. It is adapted from this nice tutorial on scikit-learn website. So during the for sure, I assume you know about Colab. If you don't know about it, Colab, you can reach it through Google. If you don't remember the URL, so you write Colab, you open Google Colab. So it is a cloud development platform. So if you use it, you are able to create notebooks. In these notebooks, you can write Python code that will be executed on a remote machine, a very powerful remote machine. Not only this, but you will be able to execute system commands on that machine. You can download files, you can copy files, you can play with text files. So you have a machine, a powerful machine, having a powerful internet connection, because if you download something, it's that machine, it will use the original connection of the remote machine, which is usually fast, very fast at Google. So it is very handy to proof concepts. Please note that Colab is resetting your work after around 24 hours. I'm not sure about the exact amount of hours, but something around this. So make sure to back up your work. So for proofing concepts, for workshops like this, it is useful. But if you have a project, you shouldn't rely on Colab. And one other advantage of Colab is that the machines are powerful. They have a powerful GPU. And later on in this course, you will know that GPUs are very important for deep learning, machine learning, for deep learning training process, sorry. And GPUs are not, they are expensive, they are not cheap. And you might invest like at least 15,000 Egyptian pounds to buy a GPU, a reasonable GPU for deep learning training on the average. So it's a very handy tool. When you open it, you write a new book, or in my case, I will just upload the new book that I have just prepared. So let's upload it. It is uploading. So Colab is opening now. Yeah, and you don't have any cell is executed. In this cell, I write some Python code. If you want to write system commands, you should put a percentage symbol before it. So all of these are Python code. I import NumPy, plot library, matplotlib, because I'm going to plot the output of the clustering, the results. I use 3D axes because I'm dealing with data that is 3D. So I will plot in 3D. And from scikit-learn cluster, I will import the k-means class or sub-package. And from scikit-learn also, I will import the datasets because I'm going to import a dataset. And I set the random seed to 5 to make my code or my results reproducible. So any random choice here that involves NumPy will lead to the same result if this is fixed to 5. Okay. So I am loading from the scikit-learn datasets the iris dataset. Okay. And I'm storing its data into a variable X and the target into a variable Y. For sure, we will not use the targets because today is about unsupervised learning. So the targets here will not be used, but I will be using it to verify that our clustering result is good or not. So I will be comparing our unsupervised learning outcome with the actual labeling outcomes. Okay. So I create different k-means estimators. I create 3, and I store them into a list of tuples. And each, I have 3 tuples. Each tuple have an estimator. The first item of the tuple is a textual description of what this estimator is doing, because I'm going to call this string to print the name of the estimator. So I give it as any descriptive name. And the first estimator is having the n clusters equal to 8. This is the k. Okay. I have another estimator which have the number of clusters equal 3. And I have a third one that is also using k equals 3. But actually it is having the variable n in it as equal to 1. So n in it by default is equal to 10. So the first 2 clusters are using n init equal to 10, which is a good value. N init is actually the number of times the k-means will be run in order to take the best result as we have discussed. So by default, scikit-learn runs k-means 10 times and pick up the best result. So here we set it to 1, which is bad. This is why I name this estimator as a bad estimator. Okay. And also the initialization strategy is set to random, which is bad. So the centroids, the initial centroids are picked up in a random way, which is again not very optimal. Let's say the default value of the init strategy is what's called k-means plus plus. Okay, and k-means plus plus is a better method, and we will discuss it later after we go back to the slides. Okay, but here I put it to the bad initialization strategy. So I name this k-means iris bad init, and I have another one with 8 clusters and another one with k equal to 3. Okay, let's print some information regarding the data we have just imported. So this code is, this cell here is not run already, because you can find here that the brackets are empty. If you run it, it is running, you will find that you have a number here after it finishes that tells you that this is the first cell that you have run. So you should have one here that tells you this is the first cell that you have executed, because you know Python is interpreted language. So you can run this code, run this cell, run that cell, the second one, and come back again to run that cell, no problem. And the results outcomes is function of the sequence of cells that you are doing, because in runtime variables you might have a variable named k, and here you are increasing k by 1. So when you run this for the first time, k will be equal to 1, assuming that it started from 0. And if you run this for the second time, k will be equal to 2. So it depends how many times did you execute this cell. The runtime variables data will be decided, and in which sequence you run this. So after this has finished, you find the one here, you run the second cell. So you have two here. Now we read the data and we create our estimators. We didn't use them yet, but we just created them. We will use them later. If you, for example, run this again, this is the first cell again, you will find that a 3 is written here. And take care, this might be good, might be bad, depends on what the actual code is doing. But in our case, if you import some modules and you do the import again, nothing, no problem will happen. Okay. Now in the machines that we are using, we are investing some RAM and we are investing some memory here for the operating system and so on. And the good news is that scikit-learn was installed, because we didn't get any errors from here. If it wasn't installed, we could pip install it using a system command, which can be used in very normally in this notebook. Okay, so let's print some information about the data. What is the shape of X? What is the shape of the data? And what is the unique value of the labels? We find that the data is 150 samples, and each sample is composed of 4 features. Okay, and how many labels do we have? We have 3 labels. Okay, so let's loop over our estimators. Okay, I give names for the figures that I'm going to create, but I could have used the list of tuples that I have created, but no problem, it will work. So I loop the estimators, the name and the estimator itself. I create a figure and I make it 3D. I use the right zoom in and zoom out for it. And this is the fundamental line of code here. So for this estimator, for this k-mean estimator from my list, I call the fit function. So I give it the data to cluster, and I tell it by this line, please fit the data. Okay, so the data now is fitted, and I can retrieve the cluster labels, the outcome of the clustering, by this member named labels underscore. So labels equal estimator label.labels underscore. I have the labels for each data point stored in labels. So the size of labels is, it's a vector of 150 items. And after this, I scatter the data. They are 4D, so I will not be able to see it in 3D. So I scatter it using the first dimension, or the first feature, the third feature, and the fourth feature, and I neglect the second feature for the sake of visualization only, because we are not able to visualize the 4D data unless you draw it in 3 different graphs. Okay, and for each point, I give it a color based on the label value. Okay, so this will show us the clustering outcome from our cluster. I put some labels to the axes, and I do this 3 times. So I visualize the output of clustering from each of the 3 clusters we have. Again, we have a cluster, a clustering estimator, or a k-means estimator that clusters the data into 3 clusters with good initialization. Another one clusters the data into 8 clusters, which seems a bad choice, by the way, because we found that the actual labels of the data are 3 labels, so 3 is a more wise choice. And we have a third estimator, which is choosing a good k equals 3 clusters, but it uses a bad initialization in terms of making it random initialization, not based on k-means plus plus, and in terms of doing the clustering only one time instead of doing it 10 times and pick up the best value. Okay, so let's see how this will happen, and we want to compare this with the ground truth. So here I'm just plotting the ground truth or the label y to see it. Okay, so we'll see 4 figures. The first one is for the first estimator, the second estimator, the third estimator, and the last one is the ground truth, or the best thing that we want one of our estimators to look like it. Okay, so this is the data, and this is how our k equal 8 k-means clustering algorithm is clustering them. Okay, so each color here is representing a class, and it seems that it is not very good results, as you can see. What about the second one? The second one is using the good initialization. It uses k equals 3, which makes sense. So we find that the performance is very good. And if we compare this with the ground truth labels, let's see the ground truth, you will find that the second estimator result is very similar to the ground truth. This is our results. This is the ground truth results. Okay, don't worry about the labels, about the colors. Okay, and what about our third one, the one that is using good k value but bad initialization? How does it work? Let's see. Let's zoom in. So it is good. It is not as bad as k equal 8, but it is not as good as if we do good initialization. You can see here, if you can see my mouse, we can see here some points that are not very good classified. But again, it is not very good that I judge from this perspective. I should see the data from multiple perspectives to be able to judge. And this is why comparing it with the ground truth was a good idea. So to do k-means clustering using scikit-learn, it's a very simple process, and very few lines of code can give you access to a very powerful k-means based clustering. Okay, very good. So let's talk about the initialization strategies. So the naive method is to do randomized initialization strategies, but a better option is to pick up your initial centroids from the data points you actually have. Okay, so you guarantee that you are not choosing points for centroids that are far away or something like this. So this is a better approach to pick up your initial centroids randomly from the points you have, but there is a problem to this. What is the problem? The problem is that you most probably will be choosing multiple centroids in the same true cluster. Okay? With true cluster here, I mean we have the ground truth, the correct or the ideal clustering configuration. It is composed of true clusters. Okay, and if you use that strategy of choosing your random points or random centroids as random points from the data points you have, you most probably will be having multiple centroids chosen, and they are chosen in a way that makes them lie in the same true cluster. Okay, And the reason why this is that you can calculate the probability of having centroids in unique clusters. Okay, so if you have true clusters and you have points that belong to these true clusters, and you randomly select k points, k centroids from these points. What is the probability of having these centroids you randomly selected falling in unique true clusters? You can calculate this probability given the information I give to you. It's very simple. So I will leave this as a research question for you to deliver in your assignment before we meet next time, inshallah. So to avoid this, you can rely on farthest point heuristic. So you can pick up the first point randomly from your data points, but let's choose the second point as the second class, the second centroid as the point in your data points that is farmost from your first centroid. What about the third centroid? It is the point in your data that is farmost from your data points. And if you remember, that was the technique that was used in the online interactive clustering website we have seen together. Okay, very good. So is there something better? Yes, there is the k-means plus, the one that the one initialization strategy that scikit-learn is using by default. Okay, and it is better than the options that we have discussed. The main idea is that it is trying to choose centroids based on a probability that is proportional to its distance from the nearest previous centroid. Okay, I will leave the paper for you to read, and please try to read the paper and summarize what you understand from how this method is doing as an initialization strategy, and why it is better. Okay, this is the second question. So these are some results from k-means on some data. So k-means is performing very bad in this example here. If you can see my laser pointer, because the value of k was not set properly, and k-means performance very bad despite the fact that you define k very well. K is equal 3 in this example, and it seems from what we see that 3 is a good choice, but unfortunately, because k-means is assuming spherical clusters, it is not able to do clustering of distributed blobs like this, which are that are distributed in a way that looks like ellipses, or something that is overlapping like this, or something that is inside a bigger pulp like this. Okay, it might perform good in different sized blobs like this. It is performing also well in spherical like data that is clearly separated. Okay, it is not performing well in this case as well, which is similar to this. It is performing good in this case. In that case, also it is performing not bad, but the problem is that it is doing hard assignation. It is assigning all of these points which are far away from the origin or the center of the cluster. It is assigning them with a confidence that is equal to the confidence of assigning these points which are very near to the centroid of the cluster. This is a problem with with k-mean because it's doing hard assignation. We might be looking forward to something that is doing soft clustering, something like this, something that assigns points to clusters in a soft manner. So it tells you that these points are assigned to the yellow class with 0.6%, but these points here are assigned with 99%. These points are assigned 90% to the red class, but the farther you go away from the center, the less the assignation probability you get. So we will discuss in the coming lecture, inshallah, soft clustering methods. We will discuss density-based clustering methods that is able to achieve clustering like this. It can cluster blobs, continuous blobs like this without having any problems. We will discuss hierarchical clustering methods, including single link, complete link, average link, word methods. And afterwards, we will be discussing the validation of clustering methods, how to judge whether the clustering result is good or bad in an automatic way, which is qualitative. So we will be discussing all of this during next time, inshallah. I would like to thank you so much for your attention during our lecture and your engagement during our live session. And I wish this recording is better because due to the bandwidth problems we have in our online live session. So this lecture will be more easier for you to follow up. And during these times, I wish you stay safe. And please, we are relying on your feedback regarding this whole online teaching experience. It is something that is new for all of us. It is not only new for you, it is new for us as well as faculty. So please, we are relying on your feedback. I will send you the presentation. I will send you this video recording. I will then send you the reference textbook. Please don't forget to send your assignment before we meet next time. We should meet in our next lecture next Monday, inshallah. So until then, see you next time and stay safe. Goodbye.